The Story of Computers, Part 1, From Fingers to Machines. The birth of counting minds. Long before any wire was wound, before code was ever written or circuits ever lit up, the only processor the world had ever known was the human brain. Thousands of years ago, our ancestors gazed at the sky, tracked the moon's cycles, counted the seasons, and realized something profound. Numbers were everywhere. But the brain, as marvelous as it was, could only hold so much. Imagine a tribe tracking their livestock. Sheep, goats, maybe grain. At first, they might use fingers. Then they might scratch tallies on a bone or tie knots in a rope. These were the earliest external memories, the first step toward computing. But what happens when numbers become too large, or trade becomes too complex? That's when humans began crafting tools to think outside the brain. Chapter 2, The First Computers Without Electricity. The first real computational tool known to history was the abacus. Dating as far back as 500 BCE in China and Mesopotamia, it was a wooden frame with rows of beads. Each bead represented a unit, and by sliding them, people could add, subtract, multiply, and divide, faster than with pencil and paper. Though primitive by today's standards, the abacus is still used in parts of the world. Why? Because it reflects a core truth of computing, the physical representation of logical states, something that will echo through all of computing history. In India, scholars developed the concept of zero, a seemingly simple idea that allowed for complex mathematics. It was revolutionary. Zero gave numbers place, allowed for calculations we take for granted today. The Arabic numeral system, which actually came from Indian mathematicians, eventually replaced cumbersome Roman numerals in Europe and spread through the Islamic world to the West. That mathematical clarity would later form the foundation of digital logic. Chapter 3, Gears of Logic, The Mechanical Revolution Begins. By the 1600s, Europe was in the midst of a scientific transformation. Astronomers and mathematicians needed more accurate tools. Enter Blaise Pascal, a French genius who at just 18 years old invented the Pascaline, a mechanical calculator that could add and subtract. It used a series of interconnected gears and wheels. Each time a gear turned from 9 to 0, it carried over to the next, just like modern binary addition. A few decades later, Gottfried Wilhelm Leibniz, who co-invented calculus, introduced the stepped reckoner, a more advanced machine that could multiply and divide. He even dreamed of a universal language of logic, writing, "It is unworthy of excellent men to lose hours like slaves in the labor of calculation." But the most stunning vision of a machine that could compute anything came in the 1800s from a man named Charles Babbage. Chapter 4, Babbage and the First True Computer. Imagine Victorian England. Gas lamps glowing in the fog, steam trains hissing, men in top hats debating science and philosophy. In this world lived Charles Babbage, a mathematician and inventor who hated human error. In 1822, he designed a machine called the difference engine to automate the calculation of polynomial functions, long tables of numbers used in navigation and astronomy. But as he built it, he realized something. What if he created a machine that could do any calculation, not just one type? Thus, he designed the analytical engine, a steam-powered gear-driven marvel that could take input, store memory, perform calculations, and deliver output. It had a mill, CPU, store, memory, and used punch cards to program it, all core concepts of modern computers. Though it was never completed in his lifetime due to funding and complexity, it was the first blueprint for a general-purpose computer. And then came Ada Lovelace. Chapter 5, The First Programmer in History. Born in 1815, Ada Lovelace was the daughter of poet Lord Byron, but her mind was deeply mathematical. Fascinated by Babbage's analytical engine, she translated an Italian paper about it and added her own notes that were 3 times longer than the original text. In her writings, she described how the machine could be used to perform not just mathematical tasks, but potentially even compose music or manipulate symbols, a concept that foreshadowed modern software. She even wrote what is considered the first algorithm ever designed for a machine, a program to compute Bernoulli numbers. She saw that machines could follow instructions. She understood that they could become more than calculators. They could become creative tools of logic, and that idea would lay dormant like a seed until electricity would finally awaken it. You've witnessed the birth of mechanical minds. Now we move into a world electrified by war, ideas, and ambition. The Story of Computers, Part 2, The Rise of Electrical Thinking Machines. Chapter 6, War, Logic, and the Birth of the Digital Age. The world had changed. As the 20th century unfolded, technology leapt forward. Electricity was no longer a novelty. It was the blood in the veins of cities. Lights glowed, radios sang, and deep in university labs, machines began to hum. But it was not curiosity alone that accelerated computing. It was war. In the 1930s and 40s, as the world crept toward the abyss of the Second World War, governments realized they needed faster, more accurate calculations for ballistics, for cryptography, for survival. In the calm academic air of Cambridge, England, one man's mind was already decades ahead of the world. His name, Alan Turing. Chapter 7, Turing, the man who imagined all machines. Alan Turing was strange. He was brilliant, awkward, and fiercely logical. In 1936, at the age of 24, he wrote a paper, not a blueprint or a machine, but a mathematical concept. He described an imaginary machine that could read symbols on a tape, follow instructions, and manipulate those symbols. This theoretical device, later called the Turing machine, could simulate the logic of any computer algorithm, no matter how complex. It was not built from wires or metal, but from pure logic. He had quietly invented the idea of the modern computer before computers existed. One machine, infinitely programmable, solving any solvable problem. And then came war. Chapter 8, Breaking the Unbreakable. Nazi Germany had a secret. The Enigma machine, an electromechanical rotor device used to encrypt military communications. Its ciphers changed daily, with hundreds of trillions of possible combinations. The Allies could not break it manually. Human effort had failed. At Bletchley Park, England's secret code-breaking facility, Turing led the team to build a machine that could, the bomb. It wasn't digital in the modern sense, but it was an electromechanical brain. It spun through possible Enigma settings thousands of times faster than humans could, and every time it found a possible key, it helped decode enemy messages, shortening the war, saving millions of lives. Turing, with machine logic and relentless focus, had shown the world that machines could think in narrow but incredibly powerful ways. Chapter 9, The First True Digital Computers. Across the Atlantic, in wartime America, another giant awoke. The ENIAC, Electronic Numerical Integrator and Computer. Completed in 1945 at the University of Pennsylvania, it was a monster, 30 tons, 18,000 vacuum tubes, and it could calculate thousands of times faster than any human. Unlike mechanical or electromechanical systems, ENIAC used pure electricity. It was the first electronic general-purpose digital computer, but programming it was a nightmare. You had to manually plug cables and flip switches. There was no stored program. That idea came from John von Neumann, a Hungarian-American genius who proposed a new model. The computer should store both instructions and data in the same memory. This became known as the von Neumann architecture, and it's still used in nearly every computer today. Chapter 10, Transistors, the dawn of the tiny revolution. While ENIAC was a milestone, it had one fatal flaw: vacuum tubes. They were hot, large, fragile, and consumed massive power. The future demanded something smaller, faster, and more reliable. In 1947 at Bell Labs, 3 scientists, John Bardeen, Walter Brattain, and William Shockley, invented the transistor. It was small, it had no moving parts, and it could act as both a switch and an amplifier, using tiny amounts of electrical current to represent zeros and ones. The very heart of binary logic. Transistors replaced vacuum tubes, and computers shrank from room-sized monsters to something that might one day fit on a desk. Chapter 11, The Language of Machines is born. By the 1950s, engineers could build computers faster and smaller, but they were still almost impossible to program. You had to know machine code, sequences of ones and zeros, like trying to write a book in Morse code. So came the idea of high-level languages. In 1957, IBM released Fortran, Formula Translation, the first widely used programming language. It let scientists and engineers write instructions in something resembling English. Soon after came COBOL for business, Lisp for AI, and assembly language for a slightly more human-readable version of machine code. Now, humans could command machines more easily. The foundations of software had been laid. Chapter 12: Birth of the Operating System. As computers grew more complex, it became clear that they needed a manager, something to handle files, schedule programs, and communicate with hardware. Thus came the operating system. Early systems were crude. Punch cards went in, results came out. But by the 1960s, researchers developed batch systems, and then time-sharing systems, which allowed multiple users to share a computer. At MIT and Bell Labs, a new operating system emerged in the late 1960s. Unix. Elegant, powerful, and written in the C programming language. It would become the ancestor of Linux, macOS, Android, and even influence Windows. The machine was no longer just a calculator. It was becoming a tool for creation, exploration, and expression. At this point, we are on the edge of another revolution, where computers move from labs and governments into homes, pockets, and even the human body. The Story of Computers, Part 3. The Computer Goes Personal. Chapter 13. The Microchip That Changed the World. In the quiet hum of Texas Instruments' 1958, engineer Jack Kilby soldered something tiny, something that would change the course of history, the integrated circuit, or microchip. Before this, circuits were made from individual components. Transistors, resistors, capacitors, wired together by hand. It was like building a city brick by brick. Kilby's invention placed all those components onto a single piece of silicon. It was small, cheap, and fast. By the 1970s, microchips evolved to contain thousands, then millions of transistors. These tiny rectangles of etched silicon gave birth to the microprocessor, a computer's brain shrunk to the size of a fingernail. And then came Intel. In 1971, Intel released the 4004, the first general-purpose microprocessor. It wasn't powerful, it could only add or subtract, but it marked the start of a new age, the personal computer revolution. Chapter 14. From Garage to Greatness, the Apple Story. While mainframes still ruled universities and corporations, something very different was happening in California garages. In 1976, two young men, Steve Jobs, a visionary, and Steve Wozniak, a technical wizard, built the Apple I. It was crude, no screen, no case, just a motherboard. But it was affordable and personal. Then came the Apple II, one of the first computers with color graphics and a keyboard. Unlike massive machines locked in air-conditioned rooms, it was small enough to sit on a desk. People could write, play games, or run small businesses with it. Apple wasn't selling a machine. It was selling the idea that computers could be tools for creativity and empowerment. For the first time, the public began to see a computer not as a cold machine, but as a companion. Chapter 15. IBM, Microsoft, and the Operating System Wars. IBM had watched the personal computing boom with curiosity, then alarm. It had been the king of the computing world, dominating the era of big iron machines. But now, upstarts like Apple were stealing attention. In 1981, IBM released the IBM PC, a machine that would define the computing world. It was powerful, expandable, and most importantly, open. Other companies could make compatible hardware and software, but IBM didn't write the software itself. It hired a small company led by a brilliant young man named Bill Gates. Microsoft created an operating system called MS-DOS, Microsoft Disk Operating System. It was text-based, simple, and quickly became the foundation for millions of PCs around the world. And so, a giant was born, not from hardware, but from software dominance. Chapter 16. The Mouse, the GUI, and Windows. Meanwhile, something magical was happening at Xerox PARC, a research lab that few outside the industry knew. There, engineers had invented something profound, the graphical user interface, GUI, windows, icons, and a pointing device called a mouse. Steve Jobs saw it. He didn't just admire it, he understood it. In 1984, Apple released the Macintosh, the first mass-market computer with a GUI. It was friendly, elegant, and had a voice. "Hello, I'm Macintosh." It spoke to people. But Microsoft was watching. In 1985, it released Windows 1.0, a GUI for MS-DOS. It wasn't pretty, but Microsoft improved relentlessly. Windows 3.1, then Windows 95, exploded in popularity. By the late 1990s, Windows was the dominant desktop operating system, and Microsoft the most powerful software company on Earth. Chapter 17. The Internet Awakens. While personal computers were changing lives at home and in offices, a silent revolution was brewing in universities and military labs: the Internet. Its origins stretch back to ARPANET in 1969, a U.S. military project to connect computers. But in the 1990s, something changed. A British scientist named Tim Berners-Lee created the World Wide Web, a system of hyperlinked documents accessible through web browsers. Suddenly, the internet wasn't just for academics or governments. It became a global network of knowledge, commerce, and connection. In 1993, Mosaic, the first popular web browser, made surfing easy. Netscape followed. Then came Google, Yahoo, Amazon, and eBay, digital empires built in pixels and code. The computer was no longer just personal, it was global. Chapter 18. Mobile, Cloud, and Beyond. In 2007, the world changed again. Steve Jobs held up a tiny device. An iPod, a phone, and an internet communicator. Are you getting it? He called it the iPhone. It fused a phone, a music player, and a miniature computer into one. It was sleek, touchscreen-based, and always connected to the internet. Mobile computing became the new frontier. Then came the cloud, a metaphor for servers everywhere. Instead of storing data on your device, you could use apps, games, and storage through the internet. Services like Google Drive, Dropbox, Spotify, and Netflix transformed computing from a local activity to a streamed experience. People no longer thought of computers as boxes on desks. They were in your pocket, your watch, your car, even inside your body. You've now followed computers from cogs and steam to silicon and servers. But this is not the end. This is where our story steps into the unknown, where computers begin to think, where science fiction bleeds into reality. The Story of Computers, Part 4, The Future. AI, Quantum, and Thinking Machines. Chapter 19, When Machines Began to Learn. Until the early 2000s, computers followed strict instructions. They could do only what humans explicitly told them to do. If you asked them to tell a cat from a dog, they would fail, unless you programmed every single possible feature that made a cat a cat. But then something radical emerged. Machine learning. Instead of teaching a computer how to think, engineers began feeding it examples, thousands, even millions of them, and letting it find its own patterns. This was inspired by the human brain. At its core were neural networks, tiny mathematical models loosely based on how neurons fire. Early experiments struggled, until one thing happened: data exploded and computing power soared. In 2012, a deep learning system trained on YouTube videos learned to recognize cats without ever being told what a cat was. That same decade, AlphaGo, developed by DeepMind, defeated the world champion in the ancient game of Go, shocking the world. It didn't win by brute force, but by intuition. A machine had, in some strange way, taught itself to imagine. AI was no longer a fantasy. It had arrived. Chapter 20, Natural Language, Artificial Minds. If a computer could see patterns, could it understand language? That was the challenge for natural language processing, NLP, teaching machines to read, write, and converse like humans. Early chatbots like Eliza mimicked conversation with clever tricks, but modern models use deep learning, transformers, and massive data sets. In 2018, a model called BERT transformed NLP, but in 2020, something bigger emerged, GPT-3. It could write poetry, code, stories, even pretend to be Shakespeare. It didn't understand in a human way, but its output felt intelligent. These large language models, LLMs, became the foundation of AI assistants, co-writers, coders, and artists. With models like ChatGPT, AI stepped out of the lab and into classrooms, studios, offices, and homes. Suddenly, people asked, what does it mean to be intelligent? To be creative? To be human? Chapter 21, The Quantum Dream. At the edge of our imagination lies a different kind of machine, one that doesn't just compute faster, but differently. the quantum computer. Instead of bits, zeros and ones, quantum computers use qubits, which can be both 0 and 1 at the same time, thanks to a strange phenomenon called superposition. Even weirder, they can affect each other across space through entanglement. A classical computer tries every solution one by one. A quantum computer can try all possibilities at once, in theory. Companies like IBM, Google, and D-Wave are racing to build stable quantum machines. In 2019, Google announced that their quantum computer solved a problem in seconds that would take the most powerful supercomputer thousands of years. Quantum computing promises breakthroughs in cryptography, medicine, climate simulation, and AI, but it also threatens to break modern encryption, reshaping the balance of global power. We are not there yet, but we're close. Chapter 22, The Edge of the Possible. Today, computers live in our phones, our cars, our smart speakers, and even in our toasters. We talk to Alexa, watch content recommended by algorithms, and write messages completed by predictive text. We're entering the era of ubiquitous computing, where computers vanish into the background, yet shape every part of our world. Then comes brain-computer interfaces, like Neuralink, seeking to connect human thought directly to machines. Imagine typing by thinking, or storing memories externally, or controlling drones with your mind. We're also exploring biocomputers, using actual DNA as data storage. 1 gram of DNA could hold the entire internet, and as machines become more intelligent, ethical questions rise. Can machines have rights? Can they feel? Who owns AI creations? Should AI make life or death decisions? We're no longer just programming computers. We are shaping conscious machines, or perhaps letting them shape us. Chapter 23, The Human Legacy. From mechanical cogs to glowing screens, from vacuum tubes to quantum qubits, this story is not just about machines. It's about humans. The inventors, dreamers, rebels, hackers, artists, and engineers who dared to imagine a world where metal could think. The computer is a reflection of us, our logic, our creativity, our fears, and our hopes. It is the mirror through which we see what it means to be alive, to think, to build, and to dream. And this story is not over. It continues with you.